Good morning, sir. So today, Deepthi, Saundarya, and I will be discussing stream processing using Apache Storm. We'll start with understanding what stream processing is, then move on to why the need for Storm arose, its structure and concepts like parallelism and grouping, its features, and a use case that will help us envision all these concepts in real life scenarios. So now Deepthi will continue further.
First of all, what is stream processing? Stream processing is a technology that uses the streaming data to detect the uh, conditions quickly in small period of time. The data that is generated continuously by thousands of data sources in small sizes is called the streaming data. Here the detection time is very small. It is for few milliseconds to minutes. Apache Storm is used for stream processing, and the stream processing is also known as the real-time processing. Next, when is stream processing needed? There are few insights that are not created equal. See, there are few insights that whose value diminishes very fast with time. For example, searching for most popular hashtags. Suppose if you want to search for the most popular hashtags for the past 1 hour, if suppose some X hashtag is the most famous for this hour, when the hour changes, and the value of this hashtag is no more important, like its value has decreased. Same with cricket match updates, and same with data from sensors. And there is one more thing, like if at all the data is very huge and it is not even possible to store it, you can use stream processing to retain only the useful bits and discard the remaining unuseful ones. And if at all the processing that can be done in a single pass over the data, then stream processing is a good fit for it. And till now we have learned about Hadoop, like we know that Hadoop generally works with the history data. And here in Hadoop, we store the data in the database, and then we process it and we output the results. Same way, suppose let us consider a use case. Suppose we are getting data from a temperature sensor, and here you wanted to process the data for 1 hour in every 1 minute. For every 1 minute. See, suppose if you are using Hadoop, you have to collect the data of past 1 minute. You have to store it. You have to process it. You output it, and you have to aggregate the data with the other 59 minutes, and then you have to output the answer. So this takes few minutes. But if at all you are putting few alarms for that, suppose after processing, if you consider a threshold, that is if the value of the threshold is greater than something, so you have to give an alarm. If you are giving an alarm after a minute, it is of no use. It should be very fast. So that's why Hadoop cannot be used for stream processing. So what can be used and what is used previously? We'll see to it. Nathan Mars is a person who has created Storm, and let's go into his story. He worked at Backtype, and he used to build business models over there. They used to work both on historical and real-time data. The real-time portions were implemented using standard queues and workers approach. Here, the data is sent in the form of set of queues, and workers are the Python workers who actually do the processing part. There may be two or more Python workers also, but there are many disadvantages of this queues and workers approach. First point is it was brittle, no fault tolerance, and you have to manually make sure that even every queue and worker are alive. And one more thing is that the actual business logic was very small portion of code, but the remaining serializing and deserializing logic has become more. So this makes it cumbersome. And one more thing, the logic of the application is spread across various workers, and you have to deploy it separately. This makes it difficult. Then he got a then he actually what he wanted is he wanted the whole logic to be self contained in one application. So then he came up with an idea of spouts and bolts network. Spouts are nothing but they produce brand new streams, and these streams are sent it to bolts. Here some kind of filtering and enriching of data is done. Streams are nothing but the unbounded sequence of tuples. and bolts are the ones who actually does the processing, but all the transformation of streams happens in bolts. Various functions like filter, join, transformations are done in bolts. And you can see here, when you see in Hadoop, there data is the program goes to the data and the processing is done. But here, if you see, data is going to the program and the processing is done. So that is the difference. Then the network of sprouts and bolts is called the topology. And Soundarya will discuss more about topology and grouping.
Great. Okay, let's see if my video works. As usual, it doesn't. Okay, so let me just summarize quickly what we have discussed so far. Hadoop is designed for batch processing. We all know that. The problem with batch processing is that we cannot respond in real time. And as you rightly mentioned, there are so many applications where a real-time response is warranted. And of course, we need a different kind of technology. So how does Hadoop work? Again, we have seen MapReduce. We have seen data going to the programs in the commodity hardware as mappers, and then we doing some processing there. But then this way, we are not going to get to real-time responses. So the whole architecture is in Hadoop MapReduce, at least, is designed for batch processing. That doesn't work for real-time response. So now what do we do for real-time response? We need a different kind of architecture, and the different kind of architecture brings with it a different terminology. So we got used to at least two concepts, the concepts of sprout and bolts, which comes together into what we call as a graph structure or a topology. So the whole point here is to design a topology which gives a real-time response, but it still remains to be a magic as to how this topology actually gives a real-time response. So that hopefully we'll see in the next few slides. Yeah. Is that a good summary of what you said?
Yes, sir.
Thank you. All right, let's move on.
Okay. Hello. We have seen about topology, how the topology, like it's of bolt and sprouts.
Sorry to disturb something. Can you just close that small black window on the top? So yeah, you can close that. Shouldn't affect the call. Yeah, okay. Thanks. Please go ahead.
Okay, so parallelism. What a parallelism in the topology, it's like a general term. Like here what it means, the number of instances of each component in the topology, how it is running in parallel. That concept is of parallelism in the topology. So to know that how this is installed in the Storm cluster, we need to know the three important components that is involved. That is worker process, and then executor and task. So the worker process, what a worker process is that in a Storm topology, we have, it is deployed, the topology is deployed across multiple nodes in the Storm cluster. But inside each node, we can run a multiple virtual machines. Since it is in Java, we are saying JVMs, that is Java virtual machines. And each of these virtual machines are worker process. And one more thing, if in a Storm cluster, we can run a multiple topology at the same time. But inside a worker process, it can be responsible for only one topology. We can't run a two topology on the same worker process. This gives a little bit isolation and degree of freedom between the topologies. And the next one is executor. Executor is that inside each worker process, there can be an instructor, like that is a sprouts or bolt, that each there can be a multiple threads that execute that part of the topology. Each of these are called executor. The sprouts or bolt is called as executor. And one more thing, in a topology, when we have a bolt or a sprout, it can be that work of that sprout can be done by a two or more executors are need, but an executor cannot do the work of two bolts. If at all we have two bolts that splits the sentence and the count the word, that cannot be done by the single executor. But an execute of if you take a bolt of splitting a word into sentence into a word, that can be done by the two executors. And the next one is about task. Task is the most granular part of task execution. We mean by that is inside a node there can be a multiple worker process, and inside a worker process we have a multiple executor, and inside executor we can have many tasks. But task we cannot divide it further. If at all we take a work of splitting the sentence into word, that is the work done by a task. So in here, we can see an example of a one node. And then inside that node, there is two worker process. And inside that, we have three executors. You can see the different colors of shades of gray. Each one is one executor. And inside that, each executor, we have different number of tasks. We can keep number for that executor is need not be same. It can be any number. And if at all there is two executor there in two worker process, in each worker process, we can have the different number of things. So it is user defined to define the desired level of parallelism. So by tuning the number of executors of worker process, we can decide what parallelism that is needed. And one more useful process, one is the very advantageous process of Storm, is that we can change the number of workers or executors even during the runtime. If at all we are feeling that it is very slow, we can add the worker process more or executor even during the runtime, but we can't change the number of tasks inside the executor during the runtime. So we will see how this parallelism is being conferred using a simple topology. We are taking a topology of counting a number of words in the document. Without parallelism, what we can do is that we can take inside a node only one worker, and inside that, for every sprout, we will take only one executor. And for inside every executor, we will have only one task. So task is of splitting the sentence. Task is taking the sentence and then splitting the sentence and word count and then reporting. Here, the only parallelism that is happening is that all the executors are running in the parallel at that time. Only that is happening. Suppose we can increase the parallelism in the topology by increasing the number of workers, and inside every worker increasing the number of executors for the spouts or bolts, and inside the executor we can increase that task also. So suppose if we see here, we are for the second bolt, we are increasing the task, and then we are increasing the executors for the third one. So for calculating the total parallelism that is happening inside the topology, we have a simple formula, that is number of spout task and number of bolt task. If we count, that is simply the counting the number of tasks inside the topology. If we count here, it is 11. It just gives the general idea of how much parallelism is happening. But if we see here in this one, we are just counting the number of words in the document. So like from the second one, splitting the sentence to the stream passing to the word count, we don't generally need to give the inference that how it is transforming from that one to the next bolt of word count. But suppose if the topology is not about word count, it is about calculating the distinct word and the count associated with that word, we need to be a little bit conscious about how the streams are growing from the second executor to third executor, because we have to ensure that a word, for example, A is the word, all the A in the document after from that second bolt should go to the same task in that third executor. So this means that we have to pay attention to how the streams from the second executors from the one bolt to the next bolt is going. There comes the need for stream grouping. So the stream grouping provides us the complete control over how the partition of tuples is happening between the source one to the target bolt. So how this is happening, how we should partition it so that it will fulfill our requirement. There are many types of stream grouping that is possible. We will see one by one. So the first one is shuffle grouping. So shuffle grouping is that it generally divides the tuple. Hello.
Just have a small thing to remark over here. Yeah, so we were discussing how different is stream processing in Storm from Hadoop's MapReduce, right? So here is one clear difference that you have very nicely mentioned. When we talk about map jobs, so these are jobs which have an end, right? So the job runs, the job completes, and then it's over, right? So, and then if you want to do something else, you run another job. But now we have moved to a different architecture where now we have threads running all the time. So that way these are very different from the jobs that we have in our mind. So these threads can execute something. Of course, we have these bolts and sprouts, and they are always there, and they are communicating to each other through messages. And that, I think, is one key difference, which is why we are able to do real-time communication, or we are able to respond in a real-time fashion. So we don't have to wait for a job to end, and we don't have there is no aggregation of some sort of data. There's no shuffle sorting kind of stuff happening where you have to wait for whole lot of stuff to complete, and then the data comes out, and then the user gets to see them. Is that right?
Yes.
Awesome.
Yes, sir.
Thank you. Please go ahead.
So like, let's see what about shuffle grouping. So shuffle grouping generally distributes the tuples in the uniform. By the way that uniform, we mean that suppose we have 10,000 streams and we have 10 tasks in the target executor, it divides in the uniform way that every task in the target will get 100 streams. So thereby this ensures that equal work has been given to the each task in that executor. And this can be used only if there is no requirement or data driven partitioning. For example, in the first one we are just counting the number of words in that document. We don't need to consider what is that word is about. We just need to add everything that is coming inside the stream, number of words. So we can use shuffle grouping for some addition or that type of normal basic operations. So next is field grouping. So field grouping is used when we have to partition depending upon the value of a field in that stream. For example, the second one that I said, if at all we have to distinct word and count related to that, we have to ensure that each distinct word should go to the word A should, all the word corresponding in the document A in the document should go to the same task in the target executor. That time field grouping is used. And one thing we have to ensure that suppose we are having 10,000 streams and 10 tasks, we can't make that every individual word in this one to go have the individual task in the executor. So to occupy this, we are using an hash function. The hash function is that if at all we are having only two distinct word names in the document, suppose A and B, the target task is calculated by using hash of A by number of mod number of tasks and hash of B by number of tasks. If suppose this both things will give the same value, these all the strings from the source will go to the same task in the executor. Thereby we can't ensure that every task in the executor is not used properly. So it doesn't ensure the parallelism is happening correctly. So this one thing that we have to keep in mind, that every task is not used in executor. This is mainly used, for example, for Twitter. If at all in tweets, we have to ensure that how many comments that have been done by the user. So for that, according to the user ID field name, we have to partition this one. So next one is all grouping. All grouping ensures it just takes the value from the source executor and takes all the value and then send all the value to each and every task in the target one. Where this is used is, suppose we have to ensure that in our topology, we are sending the filter parameter through one spout. And we have to ensure that, suppose I am keeping the age parameter as age. I want to filter all the strings with having the age greater than 20. Then I have to keep this parameter in each executor that is filtering the strings. For that, I have to use all grouping. I can send using the separate bolt spouts that I'm sending the signals filter parameter through that one. I have to send it to each task in the target executor. That time all grouping is used. And one more thing that where we can use this all grouping is, suppose I have been storing some data for the long time during the process. And then I found that I don't need that memory now. I have to erase all the memory that is stored in that executor. For that, we need to send signal to each and every task that is there in that executor. That time we can use this for setting the reset message. That means we can use all grouping. So next one is global grouping. Global grouping doesn't do any partition. It just sends every streams that is there in the source to the only one task that is there in the target one. This can be used, for example, in the first example, we did that word count in the document. For that, we had different executor in the before one. But in the last, we are just producing an output through a single one report thing. So for that, we need a global grouping. We are taking every stream, every output from that source one, and we are sending it to the single task in that target one. But one thing is that we can even do this without using this global grouping. We can just keep one in that executor. We can just keep only one task in the executor and it will do the same job. But there can be a case that where that we have two different way that streams are being coming from. For one way, we need this type of arrangement. But in the some other way, we don't need to have this type of an arrangement where we can use shuffle grouping also. That time we can have this. That time is mainly the global grouping is used. So next one, direct grouping. Direct grouping is a specific kind. Like it is not, if at all, the source, how the partition is happening from the source and target. It is dependent upon the type by which the source tuple is there. If at all that we want to decide, if at all I'm having data related to medicine, data related to food, data related to the person's ID, job, something like that. And we want to decide the target task depending upon what journal that this stream is about. If at all it is in food, we need to process it in a different task in the executor. If it is about medicine, I need to pass it to different task in the executor. That time we can use direct grouping. This is achieved using direct streams. How means like each executor in the each task in the target executor will have a task ID, and while emitting tuples from the source executor, we will provide that stream with the task ID, thereby ensuring that this tuple coming from the source executor will go to the corresponding task ID with that task ID. So this can be used for log streaming with that is classified on the basis of type of resources. So next is local or shuffle grouping. This is similar like shuffle grouping that we discussed in the first one. The only difference is that if suppose we are having the source tuple and the target bolt are there in the same worker process that time, and we want that if you want the shuffle grouping to be happen within the same inside the same worker process, then it is called as local or shuffle grouping. This is used because suppose we can, if at all the shuffle grouping is happening across all the worker process, this increase the network traveling. So reduce minimizing the network travel, thereby increasing the performance. We are using local shuffle grouping. If at all the source bolt and the target bolt are not available in the same work process, and we are trying to do this one, it will perform the automatically the normal shuffle grouping. So next, if at all, what all we discussed about grouping doesn't fulfill your requirement of doing this one, we can customizely design our own grouping. That is known as custom grouping. So
Right. So if I may just jump in to add one more relevant thing, the factor that matters, that counts in deciding how we design this is the data that is going through the network. So obviously we want to minimize that to as much as possible, and not only minimizing the data, and it's also about how much we bombard a specific task. If as we saw in the all grouping example, when all the data is bombarded onto one task, then it defeats the purpose of parallelizing altogether. But that doesn't mean that it's never used. Obviously, once we have reduced the data to a large extent, then we can have one task to summarize or something like that, as we have already seen in the word count example, and as you also rightly mentioned when you talked about it. So these are important, but you have to keep in mind that you don't bring a worker down by bombarding it with too much of data, right? So that's another thing. And finally, what would these tasks do is a key factor, and that kind of takes us back to the idea of topology. So we have to design it. We have to worry about how we model the entire business into different tasks, and we have to decide how many workers, how many tasks, and we have to do this in a way that it scales. So remember, if we cannot scale, then we defeat the purpose of doing all these things. So we are not, our intention is not to run everything in one machine. We want to scale, we want to have multiple workers, we want to have several tasks, and we want to do it in a way such that the network traffic is minimized, and also the bombarding of a specific worker with on a specific task is also avoided, right? So that's where the human intelligence comes in, right?
yes.
Awesome, thank you.
Okay. Thank you, sir. Next will be about features that will be continued by Deepti.
Soundarya,
Yeah. Stop.
yes. after yeah, now we have seen the Nathan MARZ has came up with uh, uh, um, a single application of network of spouts and storm, and once he got this idea of a single abstraction, then he started designing storm in December 2010. And the next concern was how should the messages pass from one sprout to other sprout or sprout to bolt. Initially he thought of mimicking the behavior of same queues and workers approach to have an intermediate broker, but these intermediate brokers have few disadvantages. This make it was huge and it is a complex piece of architecture, and there were few uncomfortable situations, and this makes fault tolerance harder, because not only we have to look after the failure of a sprout or bolt, we have to look after this failure of intermediate broker also. And it was slow because the message passing was not direct, it is going through a intermediate broker. So putting all these concerns, then he came up with an algorithm that requires only 20 bytes to track each tuple right from the sprout till the end. So this has massively simplified the design and wiped out all the above problems, and making the things way more performant. This guarantees that data is processed at least once. But when do you say data has completely processed? Let us consider a storm topology. Sprout A emits a tuple T of A, and sprout B process the tuple and emits T of AB, and similarly bolt C uh, process the tuple T of A and emits T of AC. This T of A, T of AB, T of AC is called a tuple tree of T of A, and once all the three tuples are processed, then it is said to be fully processed. If at all at least one is not processed in a stipulated time, then it is said that it is not processed. Once it is said it is not processed, then sprout A is rerun again. So how do you know that? Like once it is completely processed, an acknowledgement is sent to the sprout from where it has from where the tuple has started, and if at all it fails, the same thing is sent to the sprout that it has failed, so that it has to run again. This guarantees that Storm will process the data at least once, but at least once doesn't. Hello.
Yes, just to add one more thing in the previous slide. So we will often see this kind of a design where someone is interested in knowing whether somebody is working or not. So let's say I give a task to Deepthi to do, and Deepthi is working on it. Let's say one day goes, I didn't get any response, and then I wait. And then let's say second day also passes by, I still don't get a response. Now it's very natural that I get a concern. Is Deepthi actually working on it or not? Then how do I know this? So I start poking Deepthi. I say, Deepthi, are you alive? Yeah, she says, yeah, I'm alive, I'm working on it. And then I wait again for 1 day, 2 days, again I poke her. So this is the whole idea of knowing whether a process is alive or not, and if the process is actually doing its job, and you don't know how long the job is going to take to complete. Now this whole pattern of sending heartbeats and checking whether another person is alive, and ensuring that that process is actively working on the task that you are giving. So this is what we call as a watchdog pattern, and this watchdog pattern we will see in many different applications. Even Hadoop uses this, the job tracker, when it talks to the task trackers. They use this watchdog pattern to see whether the nodes, the data nodes, are alive or not. The same idea is used here as well. Yeah, thanks.
Okay. Next here, Storm ensures that it does the processing at least once, but this at least once is a like if at all something fails and it has to rerun, then the processing, the same tuple is run again, and it is stored again in the database. So this is not efficient. So so exactly one semantics is important, that is achieved by Trident in Storm. This it is a Trident is a high level abstraction for doing real time computing on top of Storm, and this has exactly one semantics, and it has low latency distribution querying. And how does it do here? Exactly once doesn't mean that tuple is processed exactly once. It means that it is effectively reflected only once. There are various methods, deduplication, checkpointing, for doing exactly one semantics that you can see in the link if you want to know more about it. And the next point is, till now we have got the exactly one semantics. If suppose something is failed, we came to know that it has to restart again. But who is the one who will restart the sprout again? So there are few demons in Apache Storm, Nimbus and supervisors, and who take care of supervising all the nodes. First one is Nimbus. Nimbus is the master node in a Storm cluster. It is present only on a single machine. At any point of time, Nimbus is present only in one node, and its main responsibility is to distribute all the application code to various worker nodes. Worker nodes here are nothing but supervisor nodes, and it is fail fast. It is designed to be fail fast because that all the data in the Nimbus is stored in the ZOOKEEPER. If suppose Nimbus dies, ZOOKEEPER will restart the Nimbus on another node, and the data is not lost because the data is in the ZOOKEEPER, and everything will work as if nothing has happened.
Right. So here we again go back and see some similarity between Hadoop and Storm. So now Nimbus comes and it makes it as a name node, right? So now we have a single point of failure in the name of a master. And when we are designing distributed systems, we hate this idea of having a master. The problem is that if master goes down, everything goes down, and we don't want that. So in Hadoop world, we came up with secondary name node to ensure that if the primary name node goes down, then at least we have secondary name node which will work, and we have the time to fix the primary name node and so on. So design wise, we don't like this, but you do see the similarity. We still have a master node, and that makes a lot of things simpler for us. That's one point to note. Another point is the mention of ZOOKEEPER. Whenever we are working in an anarchy, right, like 10 different people are doing their task in a democratic world and nobody is superior and nobody is inferior, the problem comes in coordination. So how will these people coordinate? So let's say all of them have to meet at a point at 10 o'clock. Who is going to kind of coordinate all of them, right? So there is no central node, and each node doesn't even know how many other nodes exist. So how is it to tell to everyone that please come at 10 o'clock? And even if it says, there is no need that the other nodes will honor that, right? So now these are all the problems that we have, and so we kind of put all these problems together into what we call as coordination issues. So whenever multiple nodes have to coordinate, again, this is something we hate to do in distributed world because it's very ugly, it's very difficult to get done. And ZOOKEEPER was invented for specifically this purpose. Now ZOOKEEPER is a service which can run on a distributed system like Hadoop, and its whole job is to manage coordination, and it also acts like a temporary store. Many people use ZOOKEEPER as a store, so you can put a small bit of data in ZOOKEEPER and later go and access that data, and you can use the ZOOKEEPER nodes as a means to share data with other nodes. So we have already seen the job tracker memory in our class, as a means to store some global data. So the same thing can be done using ZOOKEEPER as well. And that's what Deepthi is talking here about, where she says Nimbus is stateless and it stores all of its data in ZOOKEEPER. And finally, remark on statelessness. So that's a lovely thing to have. So what do we mean by stateless? Usually in a client server kind of an architecture, whenever a client talks to a server, we don't want the server to remember its prior interactions with the client. So if the client wants to establish a session and says that okay, I am this person. Now, whatever transactions I do should go to my account and not to somebody else's account, let's say. So then the server has to remember the ID of the client, when the client started communicating and all those stuff, right? So now if server starts remembering all these things, then the server becomes heavy, and we have already seen, server is like a 1 point of failure. So we don't want servers to fail. So usually the design that we follow in distributed systems is we keep the servers completely stateless, meaning they don't have to remember anything. But if they don't have to remember anything, now the onus goes on to the client. So whenever client sends a request, it has to send all the information that the server needs along with the message, along with the request, or along with the message that it sends to the server, right? So that's why Nimbus is stateless. So remember, when we are designing distributed systems, we don't like to have a master node, but invariably we have one because that makes the design simple. Coordination is really difficult to achieve in a distributed system, but thankfully we have ZOOKEEPER. We would like to store tiny bits of information along with every message or along with every request, but that makes the server really heavy, so we want to keep the server stateless. So instead we push the onus on the client to move all the data together with every request. Yeah. So pretty important details in that slide, very well covered. Thanks, Deepthi. Please go ahead. Do we still have Deepthi in, or has she dropped out? Oh yeah, so Deepthi has joined.
Yeah, a call got cut.
Yeah, maybe I talked too much that she slept in between.
No, there was network issues, so.
I see. Okay. I should fix my webcam sometimes. It's not working. Awesome. Please go ahead.
Yes, Nimbus. Next one is Nimbus is the master node, and the supervisors are the Nimbus distributes all the data to the supervisor nodes, and supervisor daemon that is responsible for creating, starting, and stopping worker process to execute the task assigned to the node. Whatever tasks that are assigned to the node, they are responsible for it to see to it that it works. And same way, supervisor daemon is also fail fast. It stores all the data in the ZOOKEEPER so that it can be restarted without any state loss. Supervisor daemon normally handles multiple work processes running on that machine. And next is the ZOOKEEPER. In any distributed application, various processes need to coordinate with each other and share some configuration information. Some Storm being a distributed application, ZOOKEEPER uses ZOOKEEPER cluster to coordinate various processes. So there is no direct communication between Nimbus and ZOOKEEPER. So ZOOKEEPER is the one through ZOOKEEPER they communicate with each other. If suppose some supervisor nodes dies, Nimbus identifies that supervisor has died. So ZOOKEEPER is the one who actually runs the supervisor on another node. So this is the and sir has explained about ZOOKEEPER, and this is the Storm cluster architecture. And the next one is Storm. The Storm is implemented in Clojure, and all the Storm APIs are 100% Java. And Storm was ensured to have very large amount of potential users because of this. And Thrift is a binary protocol that is used for cross-language communication and the topology structure is also defined in Thrift structure. That is why sprouts and bubbles can be written in any language, and due to the wide use of thrift in Storm, we can write the code in any language to connect to Nimbus node. This makes Storm to be programming language agnostic. And next feature is horizontally scalable. This is a very important feature for any distributed system. And here Storm is linearly scalable, which means that you can double the processing capacity by doubling the nodes. And next one is he had made the Storm to be
Well, yes,
open source.
Yes, but only theoretically. Okay, so in theory,
Ah.
you can double the nodes and get double the processing capacity, but in practice, it never happens. And that's because of the design that we come up with. So a lot depends on how good our design is, and even with the best design, I believe it is still extremely hard. And why it is hard, we have already seen this in our distributed systems class before. It's just that achieving complete parallelism in a pseudo parallel world is just too difficult. Yeah, please go ahead.
This is a summary of features of Storm that we discussed, and keeping in mind all these features, he has built in the next 5 months. He has built his first version of Storm, and in July of 2011, Backtep was acquired by Twitter, and then he released the Storm as an open source on September 19, 2011. He left Twitter to do his own startup. And next in September 2013, he officially proposed Storm for incubation in Apache. From then it is called as Apache Storm. Later on, Apache has enhanced Storm. Then finally it was graduated to a top level project on September 17, 2014. And there are
Yeah, isn't it amazing? It just takes 5 months to come up with a product as complex as Storm, which has fundamentally different ideas, which took a paradigm shift from batch processing to real-time processing in a distributed world, with all the features of fault tolerance, making it resilient, right? And of course, making it scaling friendly, so that it's truly distributed. With all these three features, being distributed, being resilient, and being real time, right? And if all this can be done in 5 months by one person, then certainly there's no bounds or limits to what we could do in the 2 years of time that we have doing our masters, isn't it?
next.
Okay, so Deepthi agrees.
Next is there are various advantages of batch processing and stream processing. Let us once again bring back the same example that I have used, the temperature example. We get the data from the temperature, and there we have restrict processing of data for the past 1 hour. Instead of that, we are if at all we make it more generalized, if at all we want data to process for past 1 year, if at all, suppose if that is a use case, then we can make use of both batch processing and stream processing. uh, uh, Batch processing does the whatever, like speed layer is the stream processing that we have discussed what we are doing for the past 1 hour data thing. And batch processing does for every 1 hour, it collects the data and process it and stores it in service layer. Then you can query to the service, all the batch data and real data is present in service layer. You can query to it and get the data of any number of years, like maybe 2 years, 3 years old data also you may get it. This is called a LAMBDA architecture, which is designed to handle massive quantities of data by taking advantage of both batch processing and stream processing. And Buddhi will discuss about one of the use case where the stream processing is used.
Thank you.
Okay, so now that we have a basic understanding of the functioning of STORM, the next question that arises is how a real-world problem can fit into STORM. How can we build a good topology? The approach to designing a topology can be broken down into 4 steps. The first
Vritti, can you please close that black window so we could see the full slide? Thanks.
The first step is to define the problem and form a conceptual solution. We need to have a very clear understanding of the problem at hand. Also, we should be well aware of the requirements of the solution we come up with in terms of speed and space. Now we need to form a conceptual model that will outline the basic steps to solve this problem. The second step is to map the solution to STORM. That is, we need to convert it in terms of spouts and bolts. So now we have a rough design of our topology. The third step is implementing the initial solution. This is where the coding part begins. We write codes for distinct components and then wire it all together. The last step is to check whether our topology is scalable or not, and if not, adjust it accordingly to make it scalable. So let's take a real life example and try to break it down using these outline steps. So imagine this scenario. It's a Saturday night and after a tiring week of work, you are in a mood to party and you are at a bar and you have downed your third drink, but you now feel that you don't quite like this place.
It's Corona time.
So
and you're talking about partying, huh?
Just to uplift everyone's mood.
Okay. Please go ahead. Sorry for it.
So you have had your third drink and now you feel like you don't like this place so much. So you want to go to a more popular bar where all the crowd is. So, but there are so many bars in the city. How do you even decide which one is popular? Even the latest ratings on Google are a week old and you don't want to go to a place that was popular last week or yesterday or even last hour for that matter. You want to know where the action is right now. So how do you address this problem? So you would like to have a map of your city that identifies the hot zones, that is the neighborhoods where the highest density of activities is going on in bars. So we can do this with the help of a heat map. And the good thing is that it will identify general neighborhoods, which is better than individual bars, so that you have the options in close proximity to each other in case you want to switch again. So let's form a conceptual solution for this problem. Many social media platforms have this concept of check-ins. So we have access to a data fire hose that collects check-ins for bars from all of these social media platforms. So this fire hose will emit a bar's address and a timestamp for each check-in that happens. And our end goal is to produce a geographical map with a heat map on top of it, identifying the popular neighborhoods. So one question that comes into our mind is that is this data reliable enough? This stream of check-ins doesn't reliably represent each and every single user because not everyone will check in on social media. But we can think of it as a sampling of real life. We can assume that the check-ins at bars are proportional to the actual number of people present in those locations. And also even the sample data is large enough to compensate for data loss. And any data loss is intermittent and it is not sustained long enough to cause a noticeable disruption in our service. So these assumptions portray a case of working with an unreliable data source. It mimics as if we have an incomplete data set. Next is that we want to identify the requirements which our solution should fulfill. Our core need is to give our users output in real time. The output value of our output will diminish over time. So there is no point of giving what was the popular bar 3 hours ago, because that's not what the user wants at all. So we have a very strict speed restriction here. So we don't need accuracy up to some minute level of precision. So our data is proportionately representative and that is good enough for determining popularity. So as long as we are able to get recent data quickly to our users, they'll be happy. Also, unreliable data sources do not have the ability to replay failed data points. So in this case, we do not need to worry about being fault tolerant. The second is now we need to come up with a topology. So first we need to identify what our input data points will be and represent them as tuples. Also we need to identify how our final data points will look like and then represent them as tuples. And now we need to bridge the gap between the input tuples and the final tuples by creating a series of operations that will transform them. So as I said earlier, the input
here the use of the term tuple is quite interesting. In fact, we have seen this throughout this presentation that so that's the unit of message that we pass amongst the tasks or amongst the sprouts and the bolts. But why do we call them as tuples? Well, in the RDBMS parlance, we have seen that a tuple is a row, right? So which is basically one unit which has a value for each column. And here again, if you see, this can be mapped. For example, assume time is a column and address is a column, and there are values. So one row in such a table would be 9 p.m. and 287 Hudson Street. So that way it qualifies for a tuple. And more than that kind of being a unit of transformation, it's also a unit of processing. So when one unit of information, as in a tuple, goes in, some kind of processing happens, and so bolt, let's say, does something on this, and then we get some a modified unit out. So we retain the same terminology from the RDBMS parlance. We call these as tuples, right?
Yeah. Shall I continue?
Yeah, please.
So we now need to identify how our output tuples will look like. We need a time interval, say from 9 p.m. to 9 and 15 p.m., like after 15 seconds, if we want increments of 15 seconds. And we will have a list of coordinates that occurred with list of the bars that occurred within that interval. So the bars can, the addresses of the bars can be represented as latitudes and longitudes. So as a standard form, like we will represent it as coordinates, and north and south will be plus and minus, east and west will be plus and minus. So this is a standard form to represent our coordinates. And of course, in one time interval, there will be multiple users checking into the same bar. So there will be duplicates. So this is an example of how the one of the final tuples will look like. Now we need to form our topology. First, we have a spout called check-ins. It will collect all the check-ins coming in from mobile devices and emit them into a stream. And the second is geocode lookup. That is the first bolt. It will convert the addresses of the bars to a geo coordinate. The next heat map builder. It is a second bolt, and it will keep a data structure in memory to map each tuple to a time interval and then group those tuples by the time interval. The last and the third bolt is the persister to save all our n tuples into a database. So the step 3 is to implement the initial solution. So now we start writing codes for our spouts and rules. The spout will take input as a CSV file. Time is in a Unix timestamp, that is the number of seconds passed since 1st Jan 1970, and the address is a string. So, but just for the ease of understanding, I have written it as 9 and 7 seconds PM, but it is actually a Unix timestamp. And as I said earlier, we need not worry about fault tolerance in this case, but in other cases where we need to, this is the step where we need to incorporate it. Next, bolt, we need to convert our addresses into a geo coordinates. So we use Google Geocoder Java API to convert these addresses to latitudes and longitudes.
Yes, and there is also one other important thing here. So we are interested in scaling our system. So obviously we expect more workers to come in and more tasks to be created. So that means several instances of bolts running at the same time. So obviously we want to ensure that each tuple can be processed meaningfully. right? And in a way, designing what should be on the tuple is also very important, and you should not need 10 tuples to come in order to for the bolt to do something meaningfully. So instead, it's like tuple in and a tuple out. That's the kind of design that we want for our bolts. So deciding how to split the data, how to read the data, and how to pass the data to the bolts is an important concern, and that's what our Sprout is doing, if you notice. Is that right, Ruby?
Yeah. Yes.
Thank you.
So next is the second bolt. We need to collect data in memory using a hash map. So using a hash map. So it is like a key value kind of a structure. So the key is the time at which the interval starts. We need not store the time at which the interval ends, because we know each interval is of the same length. And the value will be the list of coordinates that fall into that time interval. We can extract the beginning of the time interval by dividing the check-in time by the length of the time interval. The next bolt, we will store the output to a database, and later on we can build a JavaScript based web application that can read the heat map values from this database and then interact with Google Maps API to build a geographical visualization from these calculated values. Now we also need to define stream groupings between each components. So as we can understand that from check-ins to geocode lookup and from heat map builder to persister, random grouping is fine. So we can put shuffle grouping here. But if different tuples from geocode lookup end up going to different instances of heat map builder, then we won't be able to group them into time intervals because they'll be spread out among different instances of heat map builder. Hence, we need a global grouping here. Or else we can have.
Yes, sorry. The idea is very similar to what our partitioner was doing when we discussed MapReduce, right? So we have output from the mappers. Let's say the combiner has done its local grouping task, and now we have to wonder how to regroup them and send it to the reducers, right? So that's what we discussed in the MapReduce parlance. The idea is very similar. The only thing is now we are working in a real-time scenario where the task will never end and there are a bunch of tasks lying everywhere, and these people are communicating across each other, like from sprouts to bolts, bolts to bolts, bolts to bolts, and again bolts to bolts, and then to your database. So this is the kind of communication that is happening, and the intermediate tuples, we are worrying about how to bunch them together and send it to a specific bolt or specific task at a higher level of abstraction. So in that context, so we decide whether we want to do a random grouping, an all grouping, or whichever grouping kind of helps us. Right? Yeah. Please go ahead.
And also, instead of global grouping here, we can use shuffle grouping with single instance of the heat map builder bolt. So after combining all this together, our topology is ready to run. But is this topology scalable, and will it be able to maintain its speed requirements once the data gets huge? Unfortunately not, because it operates in a serial order. One happy user will tell 10 of their friends and this chain will continue. And so in future, our demand is going to increase exponentially, just like coronavirus. So now we need to...
That's true. Please go ahead.
Yeah. So we discussed executors and tasks earlier. So there's an additional parameter called parallelism hints while building spouts and bolts to add executors and tasks. So let's say we add 4 executors for check-ins and 8 executors for geocode lookup, and each having 1 task. We add more for geocode lookup because it takes a lot longer to process than the spout. And by default, the number of executors and tasks is equal, and that is 1 task in each executor, but we can change it. Recall rebalancing. We know that our demand is going to increase in future. So we want to add more executors in a running topology without having to stop it. But we know that we cannot add tasks. So let's say that let's set the number of tasks to a higher values, let's say 64. So it will be when the number of executors increase in future, so it will be helpful for us. Next is we have parallelized check-ins and the geocode lookup, but the heat map builder, it uses global grouping. So how does it make sense to parallelize that? So right now the heat map builder is doing two jobs. That is extracting the time interval into which a given tuple will fall and then group the tuples by time interval. So what if we can separate these two actions into two separate goals, then we can get closer to our goal of parallelizing. We can introduce a bold called time interval extractor to emit a time interval and a coordinate that can be later picked up by the heat map builder. Once we have the time interval pre-calculated, we can use field grouping so that all tuples of the same time interval go to the same task. So technically we have parallelized our topology, but we know that at any given moment, all the tuples will go into the same heat map builder because the time interval will be the same. So this parallelizing is not effective. So what we can do is we can extract the city names or locality names from the addresses of the bars which we had earlier and use this as a field to parallelize things at this level. Why do we need to talk about performance considerations so early on? There's a very famous quote by Donald Knuth that premature optimization is the root of all evil. This is indeed true in most cases, but let's look at the complete quote with the context of what he was trying to say. You should forget about small efficiencies, say about 97% of the time, but premature optimization is the root of all evil. Here we are not trying to achieve small efficiencies. We are working on big data. Every efficiency enhancement we make counts. And one minor performance block can be the difference in not achieving the performance SLA that we need when working with large data sets. So we should take care of scalability before deploying our model.
So wonderfully said.
So these are the references that we use.